Welcome to FPGA Magic. Today I'm demonstrating a 50 MHz arbitrary waveform generator. The FPGA design is like magic because we use pre-made macros. The serial port is used for control. A 2-output port is used to control the gain and offset. There are two function generator modules in here. Each one consists of two ready-made modules, a 3-output port that controls modes and frequency. There's also a predefined memory function for the arbitrary memory. There's two custom modules in here. The first is the counter for the frequency, which is really simple. And the second is the mode control. The modes are sine wave, square wave, sawtooth, triangle, noise, arbitrary waveform memory, DC plus, DC minus. The noise function was found on open cores and features a 32-bit linear feedback shift register along with a 37-bit noise randomizer on the output. The sine wave is generated by a fifth-order polynomial, which provides about 14 bits of accuracy. This polynomial is heavily pipelined, as you can see, where the letter defines how deep in the pipeline it is. The other outputs are derived from the input phase counter. The outputs of these two function generators drive a math module to provide modulation, offset, and gain functions. The math is done in fractional fixed point, either 18 or 16 bits, where the most significant bit is the sine bit. So the waveforms, gains, and offsets are all signed 16-bit integers. This is fractional math, where the values are plus or minus 1, where 7FFF is plus 1, and 8000 is minus 1. The block diagram for the math module shows that there are just a couple multiplies and adds. The first multiply is for modulation, with the second being for gain. After the addition, the value is bound checked to ensure that the value is between plus and minus 1. In fractional math, a multiply of numbers between plus and minus 1 always results in a fraction. There is one decimal point in each number, and the product then contains two decimal points, so a left shift is required on the result. In additions, the numbers between plus and minus 1, the sum can overflow, so the sum must be checked. In laying out fractional math, the numbers can be scaled to avoid overflow in the addition, much like the old analog computers. Here's the FPGA pinout for the design. I made two different output boards, an R2R ladder network and a high-speed DAC. The ladder network provided 8 bits of output accuracy with a spike at mid-scale. This is where all the bits flip from the least significant to the most significant. This is present even when using the FPGA's output registers in the I/O pins with a 255 picoseconds of variation. A high-speed op-amp actually accentuates the spike. I tried pulse width modulating the least significant bit with a little filtering, and I was unhappy with the results. So I ended up going with the DAC. Here is a picture of the DAC board, along with the schematic. The board includes an inverting power supply for minus 5 volt DC. The op-amp has a gain of 6.5, which provides an output signal of a little more than plus and minus 5 volts peak to peak. In the FPGA, the upper bit is inverted, since the DAC output is unsigned. Also, I did a little trick with the double data rate output. This provides an inverted clock at the same frequency as the input frequency, and this is used to drive the DAC. Here's the Python code used to drive a demonstration video. The code drives the function generator outputs with increasing sine wave frequencies: square, ramp, triangle wave, direct digital synthesis from memory, noise, DC plus, DC minus, and then a sine wave modulated with a sine wave. Here are a couple scope pictures at 2.5 megahertz, 1 megahertz, and the rise time of the op-amp is about 15 nanoseconds. There's an opportunity for improvement, but this is an FPGA demonstration. As always, all the files are available on our website. Thanks for watching.